Welcome to this talk on the Story Modeler system. My name is John Brush, I'm the lead architect developer, and this presentation marks the end of my time working at the Zurich University of Applied Sciences. The talk is divided into 4 parts. The first discusses the background of the project, which problems it is trying to solve, and how these problems are addressed by current methodologies. The second presents the model that I propose for solving these problems. The third examines what can be achieved with the model, especially in regards to specialized queries. And the fourth makes a few philosophical observations and touches on some issues that should be addressed in a future iteration. Let's begin by defining the problem. Stories fundamentally are written in languages, and as a result, story modeling is really a question of language modeling. But you might ask yourself, why should we bother modeling language? Doesn't natural language already do the job? Doesn't English grammar already provide a full and complete model of storytelling? Well, the answer is yes and no. For human beings, natural language is, or at least seems like, a complete model. However, for machines, natural language is full of inconsistencies and ambiguities. As it turns out, those inconsistencies and ambiguities exist for humans as well, but we are simply better at error correcting and filling in the blanks. Let's take a look at what some of the difficulties are when it comes to teaching machines to interpret human language. First of all, humans are capable of dealing with linguistic ambiguities. We do this by intuitively and effortlessly weighing a number of competing interpretations as a basis for choosing the most likely in a given context. In addition, we are able to use our imagination to fill in the blanks that inevitably occur in the course of natural storytelling. Secondly, we have what might be described as a holographic memory of words and concepts. These are stored in our minds as spatially and temporally overlapping collections of images, sounds, tastes, smells, and sensations which we associate with words and from which we extract meaning. Thirdly, humans have an ontological framework for understanding language. So, for example, a car is a kind of vehicle that has 4 wheels, an engine, and a steering wheel. We know that there are other kinds of vehicles, and we know that the word automobile is simply another word for car. Finally, we have the ability to track the identities of persons, places, and things, even as they are referenced in different ways throughout a story. The current iteration of the story modeler system puts forth ideas for dealing with linguistic ambiguity and ontology, as these are the most important aspects for advanced searches. Holographic memory and identity tracking, while fascinating to ponder and undoubtedly relevant, are beyond the scope of this investigation. Let's begin by taking a closer look at linguistic ambiguity. Consider the simple statement, "He saw the table." Most likely, you will immediately think of a piece of furniture. But what if I told you that he is an accountant? In that case, table might refer to a spreadsheet or some similar two-dimensional representation of data. But what if he is a cowboy on the plains of the Southwest? Then table might refer to a geographical feature, such as a mesa or plateau. In yet other contexts, table could refer to a backgammon board or the face of a violin. All of these and more are meanings invoked by the word table, and the notion of a single word referring to multiple meanings is known as lexical ambiguity. Even humans cannot resolve such ambiguities without sufficient context, how much less so than machines. Now consider the statement, "We saw her duck." This could be interpreted either as "We saw her perform the action of ducking," or "We saw an aquatic bird that belongs to her." In the first case, her is a pronoun and duck is a verb. In the latter case, her is a determiner and duck is a noun. This is called syntactic ambiguity, since it is a syntactical function of the words within the sentence that determine the meaning. Finally, consider the statement, "I saw Mary in New York before she claimed that she would arrive." This could mean either that I saw Mary before she claimed, or that I saw Mary before she arrived. This is known as a temporal ambiguity, and stories told in natural languages contain many such instances. Turning now to the issue of ontology. Consider a sports car, more specifically, a Bugatti Veyron. The Bugatti is a kind of hypercar, which is a kind of sports car, which is a kind of car, and so forth. These relationships are hyponyms, which correspond to the notion of generalization in object-oriented design. Furthermore, The word car is synonymous with the word automobile. This belongs to the synonym-antonym group of relationships. And finally, a car has 4 wheels, an engine, and a steering wheel. Of course, some cars, such as the Reliant Robin, have only 3 wheels, but for the purposes of this discussion, and for the honor of car lovers everywhere, we shall consider 3-wheeled vehicles non-cars. In any event, the notion of composition is a well-known concept within object-oriented design. I should mention at this point that ontologies of natural language are a fairly well-researched subject and are not really the focus of this project. The story modeling prototype does include a method for defining ontologies, but this could be replaced by an external system in a future iteration. I would, however, offer the observation that both object-oriented programming and particularly the ideas on composite structure modeling put forward by UML2 could be pertinent to further exploration of linguistic ontologies. One of the key requirements in this particular project is the ability to search for occurrences of events in a particular order within a story or set of stories. Consider the following 2 stories. A dog chases a cat up a tree. The tree falls over and the cat dies. A dog chases a cat into a house. The house catches on fire and the cat dies. Now we might want to identify all stories in which a dog chases a cat and then a cat dies. Or we might want to identify all stories in which a dog chases a cat and then a tree falls. A normal full-text search would simply treat the stories as a stream of characters and would not have knowledge of the order of events. However, this is exactly what we would like for our system to do. Now I should say at this point that being an experimental project, there was no requirement for the system to understand existing stories or for users to be able to describe stories through natural language directly. As a result, the model and subsequent interface is, though related to natural language, not actually natural language. Google, Microsoft, and others have, as I'm sure you know, invested heavily in natural language processing research, and competing with those companies is not my intent. Nevertheless, techniques such as machine learning could play a role, and I will point out potential opportunities as we go along. One final disclaimer. I am not an expert in the field of natural language processing, and the ideas that I am presenting here today are largely of my own invention. From a very brief survey of the literature, I am aware of some overlap with existing research and technologies. However, there may well be more that I am not aware of. With that said, let's now dive into the meat of the matter. Upon considering a number of possible alternatives that included modeling stories as UML activities and employing neural networks, I finally settled on the following approach. The key idea is to meld the intuitiveness of natural language with the formalism of a computer programming language. The result is a kind of hybrid computer-natural language in which the ambiguities of natural language are diminished or vanish while still retaining its intuitive power. To illustrate this hybrid language, which I will refer to henceforth as simply SM, I'd like to show you some example English sentences and how these can be expressed in this language. Let's begin with this sentence. The dog chased the cat. In SM, this would be expressed as dog chase cat. The numbers in parentheses refer to specific definitions. Don't worry about them for now. We'll take a closer look at these when we delve into dictionaries. In SM, as in English, a story consists of a number of consecutive sentences, each punctuated with a period. All words are written in lowercase, partly because capitalization doesn't contribute much to the meaning, and partly to distinguish normal words from special keywords in the SM language. The sentence structure also follows the basic English sentence structure of subject, verb, and object. SM uses the order of words to determine their function in the sentence, where the subject is expected to occur before the verb, which in turn must come before the object. Sentences in the passive voice such as, the cat was chased by the dog, are not supported at this time. I kept the grammar simple for now, since the main goal was to investigate basic principles. However, the grammar could easily be elaborated. A further constraint is that SM does not support articles. Thus, the dog and the cat simply become dog and cat. Also omitted are flexions, including conjugations, comparisons, and declensions. Thus, chased third-person past tense becomes chase first-person present tense. As we will see shortly, no tense other than the present is required, as time is handled differently in SM than in English. Finally, pronouns and plural forms are also supported. Thus, The dog chased it cannot be directly expressed. However, it is possible to rewrite the sentence as Minnie dog chased cat, where Minnie is a determiner relating to dog and cat is a specific noun. The language does, however, support adjectives and adverbs, so phrases such as mad dog, clumsily chased, and frightened cat can be written. SM also supports prepositional phrases, both of nouns and of verbs. So, a dog may have a collar, a chase may go up some stairs, and a cat may belong to a neighbor. Notice that the verbal preposition upstairs occurs after the verb rather than at the end of the sentence. Prepositional phrases must occur immediately after the associated noun or verb to avoid ambiguities. Prepositional phrases may also include adjectives, so the collar of the dog may be green. Furthermore, multiple nouns, verbs, adjectives, or adverbs may occur in the same function. So for example, dog becomes dog and raccoon, chase becomes chase and scare, mad becomes mad and bad, and clumsily becomes clumsily and half-heartedly. Compound words such as hot dog must either be written as one word by using a dash or by using quotes. So far, we have seen examples that contain subject, verb, and object. However, sentences in SM may omit the subject and or object. For example, a passive formulation such as the cat was chased is expressed simply as cat chase. This may not seem intuitive at first since we are used to expressing the passive voice in a different way, but it actually works and is entirely consistent if you think about it. This is where we begin to see the programming language aspect of SM outweighing the natural language aspect. With some practice, as with a new programming language, a sentence such as chase cat can be read and interpreted quite easily. Anyway, we can also express the dog chased as dog chase, and chasing occurred as simply chase. SM offers one final grammatic construct, which is the ability to formulate complex sentences by joining multiple clauses with a conjunction. The problem with conjunctions is that they often, if not always, imply something about the ordering of events in time. So for example, if I say, the dog chased the cat and the cat chased the mouse, I'm implying that the chasing took place simultaneously. Whereas if I say, the dog chased the cat because the cat taunted the dog, the implication is that the taunting happened before the chasing. In the next section, I will discuss the language's model of time, why conjunctions pose a problem, and how they could be addressed in a different way. So far we have seen how the SM language defines stories at the sentence level. But of course a story is more than a single sentence. In natural language, you string sentences together into paragraphs, paragraphs into chapters, and chapters into stories. If the storytelling style is simple, then the ordering of sentences roughly follows the order of events of the story. I say roughly because even the simplest stories harbor many exceptions to this rule. Consider this snippet of the story of Red Riding Hood. Little Red Riding Hood walked through the woods. Her mother had cautioned her about the dangers, but she forgot as she began enjoying the flowers and butterflies. The past perfect tense of the verbs had cautioned tell us that the cautioning took place before Red Riding Hood's walk, even though the sentences are in exactly the opposite order. Furthermore, it is understood by the context that Red Riding Hood is walking while she is forgetting and enjoying. If we were to draw a UML activity diagram, this is what it might look like. First, the mother cautions Red Riding Hood. Then, two lines of activity unfold at once. The first is that Red Riding Hood walks through the woods, and the second is that she forgets the warnings and then proceeds to enjoy the flowers and butterflies. The arrows indicate a temporal relationship from an activity that occurs earlier in time to one that occurs later in time. The straight bar, known as a fork node, indicates a point from which multiple parallel lines of activity may emanate. While this version of the story is certainly less literary, it has the advantage of being very explicit about the ordering of events in time. One important consequence of this model is that verbal tense is no longer required, and this explains why the SM language only supports the present tense. The activity at any given point is expressed from that point's vantage, which is, of course, always the present. Furthermore, Each activity corresponds to a discrete behavior and thus to a discrete verb. You will recall that I mentioned previously that conjunctions are in conflict with SM's time model. This is because each clause in a sentence contains its own verb and thus corresponds with a discrete activity that, depending on the conjunction, may lie in the past, present, or future. The temporal semantics of the SM language are analogous to UML activities. The rules are this. For any two consecutive sentences, the sequential order of the sentences in the story corresponds to the chronological order of the events they represent. So for example, here the cautioning takes place before the walking, and the forgetting takes place before the enjoying. If, however, two sentences or blocks of sentences are connected using the while keyword, then those sentences or blocks are understood to happen in parallel. Thus, the walking takes place in parallel to the forgetting and enjoying. Note that blocks are denoted by parentheses. In this case, the parentheses around Red Riding Hood walked through woods is actually not necessary, since the while operator applies to the immediately previous and or following single sentence by default. Parentheses are, however, required when the while operator should apply to multiple sentences. Some subtleties of the language are best understood by imagining a clock for each story thread. One tick of the clock corresponds to one event or sentence. For example, the story thread S1 has one tick corresponding to the walk event. By contrast, S2 has two ticks, one for the forget event and one for the enjoy event. The ticks serve to define an order within a given story thread. However, they do not allow for inferences in regards to absolute time. Thus, the forgetting might have taken 5 minutes and the enjoying 50 minutes, or vice versa. The only thing we know for certain is that the sum of all events within S1 takes the same amount of time as the sum of all events within S2, since S1 and S2 are parallel threads. Now imagine adding a second event to the S1 story thread. We know that the running will occur after the walking and that the enjoying will occur after the forgetting, since the order of events within a given story thread is deterministic. We also know that the walking and forgetting will begin simultaneously, and that the running and enjoying will end simultaneously, since S1 and S2, being parallel threads, must begin and end at the same time. However, what if we want to know which begins first, the running or the enjoying? There is no way to tell, since the order of events between parallel threads is undefined. It is possible that the running occurs before the enjoying, after the enjoying, or at the same time as the enjoying. Taken a step further, parallel sets of story threads may be regarded as a single step within a containing thread. So for example, the entirety of S1 and S2 are regarded as a single step and thus tick within S3. You can think of this fork and merge step as a kind of synthetic event within S3 that, from its point of view, is the same as a regular event such as caution. Note that every story in the SM language begins and ends with a single thread, known as the root thread. This is true even if the story fundamentally consists of parallel threads. In that case, the root thread will immediately split into multiple threads which then merge immediately before the root thread terminates. So far, I have shown you the grammar of the language and how stories are constructed from sentences and story threads. Now I want to turn your attention to the issue of ontologies, or dictionaries, as they are known in SM. You may recall that the first example I showed you had numbers in parentheses after each word. These numbers correspond to specific definitions within a dictionary that is also specified in the SM language. For example, in the dictionary Standard English, the entry dog might have 3 definitions. Consequently, the expression dog1 refers to the definition 1 of entry dog. If we change dog1 to dog2, then the meaning of the sentence would be, the hot dog chases the cat. If we changed dog2 to dog3, then we would get a compiler error, since the third definition refers to a verb rather than a noun, and multiple verbs, at least in this way, are not allowed. One reason for referring to specific definitions rather than merely the words themselves is to eliminate lexical and syntactic ambiguities. Thus, sentences such as he saw the table and we saw her duck are semantically deterministic. Another reason is to determine the function of the word in a sentence. For example, here definitions 1 and 2 refer to nouns, whereas definition 3 refers to a verb. As a side note, SM is a so-called context-sensitive language, since the production rules cannot be resolved by syntax alone, but rather rely on the meta-information provided by definitions. But dictionaries do more than simply resolve ambiguities in the grammar. They also form the basis of an ontology that defines the relationships between words, including synonyms, antonyms, hypernyms, and hyponyms. Other types of relationships, such as homonyms, which are based on pronunciation, are not part of the language. Notice that the relationships point to specific definitions. For example, a synonym of dog is the definition hound one. Normal dictionaries usually only reference a given word, but not a specific definition. As we will soon see, the ontology provided by dictionaries is critical for the way in which queries are executed. Besides standard language dictionaries, it is also possible to define domain-specific dictionaries that either introduce new words or redefine existing ones. For example, the standard dictionary might contain the word bruise, whereas the medical dictionary might introduce the more medically precise contusion. Or the standard dictionary might offer a general definition of the word amputate, whereas the medical dictionary might redefine amputate using more medically precise terms. A dictionary may declare its dependency on one or more other dictionaries via the use keyword. Dictionaries are used by stories to define a narrative. For example, here, the Fun with Sharp Instruments story uses the medical dictionary. When a story uses a dictionary, it also uses any dictionaries used by that dictionary, and so on up the chain. Therefore, by using the medical dictionary, Fun with Sharp Instruments also transitively uses the standard English dictionary. If a word exists in more than one of the dictionaries used by a story, then word resolution is performed by going up the chain of dictionaries where the first definition encountered wins. So, for example, if amputate is defined in both the medical and standard dictionaries, the medical definition wins because it is the first in the chain. On the other hand, words such as contusion and dog must be resolved by the medical and standard dictionaries respectively, since they are only defined once. I should also mention that it is currently possible to define anonymous private dictionaries that are strictly local to a given story. I mostly use this as a way of dealing with personal pronouns and dates and times, but I suspect that there is a better way of addressing those issues. For example, here the personal pronoun Zaphod Bibelbrox is defined as a hyponym of man. The private dictionaries proved problematic in conjunction with queries, as I shall discuss later. Another noteworthy feature of dictionaries is that you can choose to define words either by flat text or by sentences written in the SM language itself. For example, the definition of the word dog can be either an unstructured string with no deeper meaning for the system, or structured data in the form of sentences written in the SM language itself. The advantage of these structured data is that it provides a richer ontology to draw upon during, for example, queries. Ultimately, I think that the structured definition would be the way to go. However, you do have a bootstrapping problem since words are defined by words that are defined by other words and so forth. More formally, the problem is one of cyclic dependencies, and you would have trouble figuring out where to start. By providing a way to define words in isolation, I was able to sidestep the bootstrapping issue. I should mention that the idea of natural language ontologies is one that is well researched and is embodied in existing systems. For example, the WordNet database by Princeton University performs a very similar function, and to the degree that an overlap exists, the Princeton system is almost certainly the better choice. One possibility would be to replace the story modeling dictionaries with a component that accesses the Princeton database. Another would be to simply write an import function. In any case, if the prototype is actually ever taken a step further, using an existing ontology is clearly preferable to writing a new one from scratch. Now you might be saying to yourself at this point, "Dear God, John, do you really expect people to specify the definition of each word, of each sentence, of each story that they write?" Well, in a sense, yes, because SM is designed as a programming language that removes the ambiguity of natural language. However, as any modern programmer knows, writing code in a simple text editor is a very different experience from writing code in an IDE such as Eclipse. Features such as syntax highlighting, command completion, and refactoring enable developers to think less about the coding mechanics and more about the overall design. In the same spirit, a fully featured SN tool would provide a number of ways to simplify working with stories, while the language itself would remain precisely defined. Hopefully, this would pave the way towards adoption. For example, one can imagine a UI that suggests possible matches to partially entered words based on the current context. Thus, entering the letters D and O would prompt the system to suggest words such as doctor, dog, doll, etc. Whereas opening a parenthesis would prompt the system to suggest possible definitions of that word. The system would only suggest words with functions that apply in the current context. For example, given the sentence fragment dog chase, typing C would produce a list of adverbs, adjectives, prepositions, and nouns beginning with C. Verbs and conjunctions would not be included in the list since they are not possible here by the rules of the grammar. Taken a step further, the system could apply some form of artificial intelligence to try and determine the intended definition with little or no user intervention. Rather than simply pointing to a specific discrete function, it might make sense to list multiple definitions, each with its own probability. Furthermore, the definition references could be linked with logical operators such as AND, or XOR. XOR represents the way we normally use language, which is to say that we usually intend a specific meaning with a specific word. However, poetic language often references multiple meanings simultaneously, and logical AND and OR could be useful for this purpose. We now come to the key application, which is the ability to find stories that contain a particular sequence of events. Consider the following three stories: dog chase cat, gorilla chase cat, and gorilla chase monkey. In the simplest case, a query consists of a single clause. Here, dog chase cat will match the story S1 but will not match S2 or S3 since the subject of those sentences is gorilla rather than dog and the object of S3 is monkey rather than cat. Query clauses follow the same grammar as story clauses. So, for example, it is possible to omit the subject in the query, leaving only the verb and object, chase cat. The results of this query are S1 and S2, since both contain clauses with a verb and object that match the query criteria, whereas the object monkey of S3 does not match cat. Taking this a step further, we can simply specify the verb chase, resulting in all three stories matching. The power of the query engine lies in its linguistic intelligence. For example, here the query matches S1 but not S2, since chase in the query is a predicate, whereas chase in S2 is an object. In other words, the functions of the words in the query must match those in the story. If no adverb is specified in the query, then the engine will match any clause that contains the specified verb. So, for example, chase matches both S1 and S2, while quickly chase only matches S1. More generally stated, for a match to occur, the set of words specified by the query must be a subset of the set of words specified by the story. In this more elaborate example, you can see that the words mad, dog, chase, up, stairs, and cat all occur in S1. The fact that the dog is also bad and has a collar, and that the cat is sly and fast and belongs to the neighbor is irrelevant for the matching engine. The grammar awareness is something that sets SM apart from a normal search engine. Just think how difficult it would be to achieve the same result with, say, regular expressions, which are not aware of the functions of words in a sentence. Another important feature of the query engine is the ability to use dictionaries to identify closely related words. For example, here the query asks the engine to consider not only direct matches of the words person, drive, and car, but also any hyponyms of those words. Thus, both woman and man match person, while Bugatti Veyron and sports car match car. By specifying include hyponym, not only the direct hyponyms of the specified words are included, but also any descendant hyponyms. For example, the direct hyponyms of car might include hatchback, sports car, and Formula One car, each of which may have its own hyponyms. Thus, a sports car may be a sports sedan, a supercar, or a muscle car. Hypercar is a kind of supercar, and Bugatti Veyron, McLaren F1, and Ferrari LaFerrari are kinds of supercar. By simply specifying the word car in the query, we implicitly include the entire tree of descendant hyponyms. Note that Bugatti Veyron, McLaren F1, and Ferrari LaFerrari are probably more accurately defined as proper nouns, but the grammar doesn't currently support these. As I said before, introducing a better way to handle dates, times, and names would be an important consideration for a future iteration. It is also possible to direct the query engine to consider all synonyms of specified words. In this case, guy and individual are synonyms of person, while automobile and vehicle are synonyms of car. Thus, person drive car matches both S1 and S2. Unlike with hyponyms, synonyms are not considered recursively. This is because synonyms don't actually form trees, but rather sets of semantically interchangeable words. Ideally, at least, every synonym of a word should point back to that word as a synonym itself. Therefore, recursing through the synonyms of synonyms would result in an infinite loop. Finally, it is possible to direct the query engine to take both synonyms and hyponyms into account. For example, here, woman and Bugatti Veyron are hyponyms of person and car, while individual and vehicle are synonyms. So far, I have only shown you examples in which a single query clause was specified. However, the query engine also supports a number of operators that support more complex searches. Consider the following stories. Dog chase cat, cat run up tree, dog bark at cat. Dog bark at mailman, mailman run away, dog chase mailman. And dog bark at reflection. One example of a compound query expression might be to look for all stories in which a dog both chases and barks. This results in matching the stories S1 and S2. Note that the order of events is irrelevant. Thus, in S1, the dog first chases and then barks, whereas in S2, the dog first barks and then chases. SM defines three logical operators, including AND, OR, and XOR, which function the same as in any programming language. Thus, the OR operator matches all three stories since all three contain at least one of the phrases, while the XOR query only matches S3 since that is the only story in which a dog is either chasing or barking, but not both. As you might expect, it is also possible to create complex expressions using parentheses to specify precedence. For example, here we are looking for stories in which a dog is either chasing and barking or chasing and whimpering. Besides the logical operators, there are two other types of operators which I've dubbed temporal operators, since they define a relationship between their operands in time. The first of these is the then operator, which defines a sequential relationship. So for example, dog chase then dog bark matches S1 since S1 uses the clauses in that order, while dog bark then dog chase matches S2 since there the order is reversed. Things get more complicated, however, when the then operator is combined with other operators. Consider these two stories. Dog chase cat, dog bark at cat, cat turn on dog, dog whimper. And dog chase cat, owner shout at dog, dog whimper, cat scratch dog, dog bark at cat. Here we are looking for stories in which a dog both chases and barks before whimpering. The key word here is before. That is, the chasing and barking must both occur before the whimpering, otherwise the story won't match. Thus, S1 matches, whereas S2 does not, since in S2 the barking occurs after the whimpering. But what about parallel story threads? Consider this example. in which a dog chases and drools in one story thread, while a dog barks and whimpers in another. According to the SM time model, the ordering of events in T1 and T2 in relation to each other is undefined. Thus, it is impossible to know whether the whimpering occurs after the chasing or not. As a result, this story cannot match. However, if the whimpering takes place after the two story threads have merged, then the chronological order is established and the query will match. More generally, when evaluating the then operator, the query engine determines the point from which the evaluation of the right operand makes sense by finding the highest common descendant of all nodes matched by the left operand. So for example, if A and B are the set of all nodes matched by the left operand, then the highest common descendant is the merged node M1, and since C follows M1, the query matches. However, if A and D are the set of all nodes matched by the left operand, and the highest common descendant is M2, and since C precedes M2, the query does not match. But what if B occurs in two different story threads? For example, here B occurs in T2 and T4. If the query engine happens to match B in T4 first, then the highest common descendant is M1, and all is well. However, if the engine happens to match B in T2 first, then the highest common descendant is M2 and no match will be found. To address this, the engine actually considers all possible matches of the left operand when evaluating the then operator. As you can imagine, this can result in a large number of combinations depending on the complexity of the left operand as well as the complexity of the story itself. Moving along, let's take a look now at the other temporal operator, the while operator. Consider these two stories. Dog chase cat, while dog bark at cat, and dog chase cat, dog bark at cat. Whereas the then operator specifies that its operands must take place sequentially, the while operator specifies that its operands must take place simultaneously. So in this case, the query matches S1 but not S2, since S2 defines the events as happening in sequence rather than in parallel. Now consider a slightly more complex case containing 3 parallel threads rather than just 2. To evaluate whether this story matches the criteria, the engine must consider all possible combinations of story thread pairs. So for example, it might take T1 and T2 and then see if T1 contains dog chase and T2 dog bark. Since neither operand matches, it then reverses the operands comparing T1 with dog bark and T2 with dog chase. In this case, T1 does actually match dog bark, but T2 does not match dog chase. And so the engine continues on to the next pair, T2 and T3. Here again, there is no order in which both sides match. It then continues on to the last combination, T1 and T3. A match is found and the evaluation is complete. But it doesn't stop there. Consider what would happen if the left operand was a compound expression. Merely looking at pairs of threads is no longer enough, since the AND expression can never match a single thread. What is required then is to look at pairs of thread groups which are compared to the left and right sides of the while expression. For example, when we compare the left side of the where expression to T2 and T3 and the right side to T1, then we have a match. More formally stated, we may say that given a set of parallel story threads, S equals T1, T2, and T3, the evaluation of the expression A while B requires splitting S into all possible combinations of 2 subsets and then applying A and B to each combination. For example, here we see that for the combination C equals 1, U1 is the empty set and U2 is T1, T2, T3. For C equals 2, U1 is T1 and U2 is T2, T3, and so forth. In mathematical set theory, the set of all permutations of U1 is defined as the power set of S. Notice that U2 is, by definition, always the complement of U1 and S. The algorithm then begins with C equals 1, evaluating the operand A against U1 and B against U2. If the result of both evaluations is true, then a match was found and the algorithm is finished. Otherwise, it continues with C equals 2, C equals 3, and so forth until it reaches C equals 8. If after C equals 8 no match was found, then the result of A while B for the set of threads S is false. In other words, there is no match. Note that the result of evaluating the empty set against either A or B is always false. For this reason, the combinations C equals 1 and C equals 8 need not be evaluated and are in fact omitted in the actual implementation. As you may suspect at this point, the size of the power set, which is equal to the number of combinations, grows exponentially with the size of the set itself. As a result, with each story thread added, the number of combinations to evaluate doubles. To what degree this actually proves important in the real world remains to be seen, but it is worth noting that one can easily imagine stories with enough parallel threads to bring the system to its knees. Consequently, an initial implementation might need to limit the number of parallel threads to avoid such issues. Future investigation might bring relevant optimization strategies to light. And so we finally come to the part of the presentation where I reflect on what I have learned and provide some insights to ways in which these ideas could be developed in the future. To begin with, I'd like to point out some shortcomings in regards to what can be modeled in the SM language and how this could be improved. To make things easy, let me begin by describing the nature of the universe. Fundamentally, the universe can be divided into the dimensionalities of space and time. Space allows for the definition of structure, while time allows for the definition of process. Space is intrinsically static, while time is intrinsically dynamic. Interestingly, all languages have similar space-time subdivisions. For example, the Unified Modeling Languages distinguishes structural and behavioral modeling, where classes are the purest form of structure and activities the purest form of behavior. Object-oriented languages also make a clear distinction between spatial descriptions in the form of classes and temporal descriptions in the form of methods. As we have seen, the SM language provides a model in which events and story threads address the temporal aspects of language with rigorous formalism. But what about the spatial aspects? And what about events that do not have a simple relationship with time? For example, in this sentence, the intention is to describe some general characteristics of the dog rather than a particular event in time. While it is possible to formulate this in SM, it is only possible to do so as part of a sequence of events within a story thread. So one useful extension would be the ability to define more static aspects of story outside of any particular timeline. In fact, if you think about some of the examples from the previous section, you might notice that a lot of the words refer to non-temporal aspects. For example, here the description of the dog as short, ugly, and wearing a collar is not limited to the event of chasing, and consequently it might make more sense for the SM language to model the dog and his properties independent of the event. And what about behaviors that do not have clearly defined locations in time? This sentence, for example, describes more a generalization or classification of an event rather than a particular event itself. Is it possible to perform then or while queries based on such data? Honestly, I'm not sure, but this is certainly something that merits further consideration. And then there's the issue of subjunctive statements such as this. The intent is to express an event that is possible, contingent, or hypothetical. One can imagine entire story threads that are purely hypothetical. Certainly, such modes of description exist in natural language. Again, I'm not certain how to address this, but merely wish to point it out as an open question. Yet another issue is that of multiple narrators. For example, in this case, the actual sequence of events is obscured by narrator bias. Was it the way he said or the way she said? Of course, in this case, it was clearly the way she said. But more generally, we have a case of mutually exclusive story threads, each associated with a particular narrator and perhaps even a certain statistical probability. Another issue closely related to modes of time is that of logic in the story model. Recall this example from the section on conjunctions. As I pointed out then, a conjunction such as because is problematic in the SM language due to the fact that the sequence of clauses is in the reverse order from the sequence of events. In cases such as this, one could imagine introducing a special keyword to define the relationship. The advantage of this would be that the events are kept in chronological sequence while still expressing the causal relationship. But what about a case such as this? Here, there is an intermediate event between the cause and the effect. Thus, the chasing was caused by the taunting, which occurred before the anger. In this case, there is no way to connect the logically related events with a keyword without putting them out of chronological order. Or consider this case in which the cause of an event is a whole series of events. Here, revenge refers to the act of chasing and biting, while framing refers to the act of scratching and fetching. In other words, there are cases in which a series of events lead to another series of events. One idea I have for dealing with this would be to introduce LaTeX-like labels and references that would allow for logical relationships to be defined independent of chronological ordering. And so, without warning, but not a moment too soon, goodbye.